So today we continue our conversation about confidence intervals, but this time instead of estimating the population proportion, right, instead of that true value that we talked about over the past few days, now the true value that we're going to talk about is the mean. So um, take a look at a quick example. Um, let's say that a simple random sample of 12 students found the SAT average for their scores for the math test was 533, and it's known the standard deviation of SAT math scores is 50 points. So what's the estimate on the average of all students who took the North Carolina SAT? So kind of like we saw yesterday, what we're going to have to do is we want to take our statistic, and we're going to add and subtract that critical value, which right now we know is Z star. I'm going to multiply that by essentially what's called the standard error, or the standard deviation of, you know, sample, if you will, right? So this time, our statistic, since we're taking means, is x bar. We still have this z star. If you recall, because we're taking a sample, the new standard deviation or standard error for us is sigma over the square root of n. So we know that um, the average for those 12 students was 533 plus or minus the z star value. Um, and we know that sigma is 50 over the square root of n, which is 12. So the only thing that's going to change is we would do a problem like this. We're just using a different value here and a different standard error, but the z stars remain the same so far. In this problem, we weren't given a confidence level, but just to kind of get the ball rolling on what it should look like. So let me get this stuff out of the way. So what do we know about sample means is what that question is asking us. Um, and what we should realize, or what we should remember, um, well, this is erasing. Um, we should remember that those x bars, if we did x bar after x bar, they are normally distributed. Remember, they should center around the true value, and they have that standard deviation of sigma over the square root of n. As long as a couple things, right? We want to make sure we still have an SRS, or we want a big N, typically 30, or we're from a normal distribution. So it could be a smaller sample size, like above. This was only 12, but SAT scores, those are actually typically pretty normally distributed. So, like we just saw, the confidence interval here will be x bar plus or minus that z star value and sigma over the square root of n. Right? So x bar should be, right, that's the sample mean. Sigma, remember, is the population's standard deviation, and n is your sample size. So if we wanted to calculate that 95% confidence interval for that last one, if I'm remembering right, that's 533 plus or minus. So the z star for 95, I'll just use the simple one of 2, or you could use 1.96, and we're going to multiply that by the standard deviation, which was 50 over the square root of 12. So crunch a few numbers really quickly. 2 times 50 over the square root of 12. So we're basically going 533 plus or minus 28.9. 533 plus 28.9. So our 95% confidence interval, 504.1 to 561.9. And so this time we would say we are 95% confident the true mean score in North Carolina is between 504.1 and 561.9. All right. So take a look at another type of example. So we take this random sample of 150 salmon from this study, and the average amount of this toxic. So there's your X bar. Right, there's your X bar. But here, we only have a sample standard deviation. That's not sigma. This is S. Construct a 90% interval for the true mean. Well, we can start kind of picking through this. It is a simple random sample. That's a lot of fish, right? I'll put them in the right place here, according to the slideshow. So, and we also know that n is greater than 30. We've got a big sample, so we don't really care about sample size here. So if we were to try to start plugging things into the formula, right, x bar was 0.0913. Z star for 90% interval, I can't recall it off the top of my head. I gotta go to the chart. It's 1.65. And then here's the issue. This is S that's given to us. We do know that we're going over the square root of 150, but our problem is we don't know this. We don't know sigma. And if you think about this for just a moment, if we don't know what the true mean is, what's the chance that we actually know what the true standard deviation is, right? We're trying to estimate this stuff about the population. So how is it that we would, how is it that we would be so lucky if you think back about this problem? If we don't know what the true average is, how would we really have access to the true standard deviation? So the solution to this is what's called a t-distribution. And it's a family of bell-shaped curves that's based on what are called degrees of freedom. Right? And degrees of freedom are associated with sample size. So, excuse me. Here's the idea with a t-distribution. It's a shifting set of normal curves. So it has a wider, a fatter tail, which accounts for increased variability. In other words, when sample sizes are smaller, we have a natural understanding that there probably is some type of, there's a lot more chance of variability in small sample sizes. So a t-distribution is actually going to take care of that for us. Degrees of freedom, a lot of times labeled DF, and what you're going to do, without going into the ins and outs of it, is basically you're going to take your sample size and subtract 1. And that's going to help us account for, bigger sample sizes have less variability. So there'll be more degrees of freedom. And the more you use this, the more familiar you become with it, it actually starts to make sense how this becomes more and more normal. So as the sample size increases, the t-distribution becomes more and more normal. So bigger sample sizes cause this curve right here to get more and more toward that normal distribution. But they all have a bell-shaped curve, and there's essentially the same application to it. But what we're going to do here, we're still using x bar plus or minus, but now we're going to use this t value, and instead of sigma over the square root of n, we're actually going to use the sample standard deviation. So we don't know sigma, so we use S, and like a t star value, if you want to put it that way. So if sigma is unknown and S is used to estimate it, then it's going to follow that t distribution. And that degrees of freedom is going to be important when we go to the table. The table is probably our best bet to figure some of this out. So we still want SRS, and there's a couple things. We want to make sure the data comes from a distribution that is nearly normal. And a lot of times we're going to look to a histogram or a box plot could give us a really good feel for that, right? So obviously your histogram should have, some kind of shape there, or a box plot. As long as there's not any really bad skewness to that box plot, it's probably going to give us a good feel for normality. So if we have a small sample, it should be nearly normal looking at a histogram or a box plot. Right, so small samples, we want to be more and more normal. If we're between 15 and 40, unless there's a crazy outlier, or which you might see in either one of the plots up here, or really heavy skewness, go ahead and use it. If data is really, really skewed, we're a little bit skeptical about using that. But if we have big samples, we've talked about this before, I'll say it again, big samples take care of everything. Um, Even if things are heavily skewed, big samples, they'll take care of themselves. So that's the idea. Um, we'll skip that. And we'll just run a quick sample with our sample from before. So we've got an SRS of 150 salmon. So there's N. There's my X bar. And then the sample standard deviation. There's S. Construct a 90% confidence interval. So we'll start to set this thing up. First things first, conditions. It is for my SRS. That's good. And N is greater than 40 here, right? Plenty of fish in the sample, so we actually don't even care about the actual shape of the real data. All right, so we're going to use a one sample T interval. All right, that's the process that we're using. And the formula for that, X bar plus or minus, I'll clean this up just a little bit, plus or minus this T star value. And we're going to use S over the square root of N. So start plugging in what we know. We know X bar is 0.0913. And then we know the sample standard deviation is 0.0495 over the square root of 150. What we need to figure out is this T star value. Well, right now, because there's 150 salmon, we know the degrees of freedom is 150 minus 1. Tricky math here, 149. If you'll go to the table, that's probably our best bet. So here is a T distribution. So the issue for us is we actually, you see right here on this left-hand side, there's degrees of freedom. The table only goes down to 100, doesn't go down to 149. So what we're going to do is we'll use 100 because it's the closest number. Now the other thing, we were looking for a 90% confidence interval. This is the beauty of this table. Confidence level, we want 90%, and we'll go to the closest one we possibly can, which is right there. So at a 90% level, 100 is as close as the table gets us to 149, 1.66. If I were to erase this, you can see as sample sizes get bigger and bigger, you can see these values actually get very, very close, 1.66, 1.65, 1.65 if we're rounding. So even at 80, degrees of freedom is 1.66. So as our sample size is getting bigger and bigger, these T star values are varying less and less. So there's the value that we're going to use, 1.66. And now it's just a matter of basically plug and chug. So we'll do the 1.66 times 0.0495 over the square root of 150, 0.0067. So we got, essentially we're going 0.0913 plus or minus 0.0067. So 0.0913 plus 0.098 is the high side of the interval, and then 0.085 the low side of the interval. So we are 90% confident the true mean level of toxins, what is that in parts per million, is in the interval 0.085, 0.098. So, a quick look at how to run with confidence intervals, whether you're using a Z star or a T star.